That takes us to our first, frankly, flabbergasting result. The unit interval is uncountable. I remember when I first heard about this result, I was like, no, that's wrong. That is not true. Georges Cantor, a German mathematician, first proved this. And perhaps unrelated to him proving this, he actually went insane. So he was the first mathematician who really started thinking about transfinite arithmetic. The fact that there are various kinds of infinities. A lot of people weren't happy with this result. In fact, to this day, there's a fair number of mathematical cranks, people who try to prove Fermat's theorem using simple means, or try to prove that the classical problems of Greek geometry are solvable, the trisecting of the angle, the doubling of the cube, the squaring of the circle. Perhaps third in the list of crank attractions, or problems that the cranks find appealing, is this, trying to show that Cantor was wrong, and that in fact the set I, the interval I, is countable. But that's not the case, as we shall see presently. Every number in this interval has a decimal representation, perhaps something like 0, decimal point, A1, A2, A3, and so forth, where all of the AI are digits between 0 and 9. Well, you know some of these representations. The number 1/2 has the decimal representation 0.5, 0, 0, 0, 0, and so forth. The number 1/3 has the representation 3, 3, 3, 3, 3, and so forth. We have to accept a few conventions. The first one that we accept is that the number 1 is the same thing as the number 0.99999 repeated, and the number 0 the same thing as this, 0.0000, and so forth. So that way we can assure that every number in here has a decimal representation. This here is a convention. If you've been around the internet long enough, you know that there's a fair number of people for whom this convention here is considered flame bait. Once we understand a little bit more about limits of sequences, we will see that there isn't much of a controversy. You could decide to use a different metric space, a different notion of distance, which would lead to a different notion of convergence, in which case 1 would not be equal to 0.9999999. But when you assume the Euclidean metric, Euclidean distance, and the usual notion of convergence, then no, 1 is equal to 0.99999 repeated. Okay, so now we've set up the problem. We are trying to show that I is uncountable. When we're trying to show that something is countable, it's easy. All we really have to do is to exhibit the order in which the elements of the countable set can be listed. And poof, we have found a proof that the set is countable. That's another way of saying that we explicitly exhibit the bijection between the set of interest and the set of integral. When we're trying to show that something is uncountable, we have two tools at our disposal. We can show that it contains an uncountable subset. That's the corollary of Theorem 8 that we saw in a previous video. Or we can assume that it is countable and show that this leads to a contradiction. And so our assumption of countability has to be wrong. It is in fact uncountable. This is the approach that we're going to take right now. Let's assume that it is countable. Then we would be able to write I as a list of points. In this case, real numbers in the interval 0, 1. Now, you and I might have different lists, but the point is we would have a list if it was indeed. Each of these points, xi, has a decimal representation, as we've just discussed. x1 would be written as 0. And I'm going to denote this by A11, A12, A13, all the way to A1n, and so forth. x2 would be A21, A22, A23, A2n, so forth. X3 would be 0.A31, A32, A33, and so forth. The general digit in the decimal representation would be A3n to remind us that we're talking about the representation of a third number. And then you could keep on going until you hit, for instance, the nth number. Then this would be AN1, AN2, AN3, ANN, so forth. Then you would continue with your list. Now we know that this set, whether it's countable or not, is infinite. Right? We know it's infinite because for every natural number, integer, n, 1 over n is smaller than 1 and greater than 0, and there's infinitely many integers, and so there's infinitely many real numbers of the form 1 over n. So we at least know that the set is infinite. So this construction here is an infinite construction. Each of these terms, aij, belongs to the set of digits 0 to 9. Possibly one of those is 1/2. So one of those could be 0.50000 and so forth. One of those could be 1/3, 0.33333, so forth. One of those would be pi divided by 4, whatever the value is. I know it's between 0 and 1, and you'd be able to write out its decimal expansion. But the assumption that we're making is that every single real number between 0 and 1 is in here. Let's revisit the assumption. If x is in the interval 0, 1, then it is on the list somewhere. That is what it means for the set I to be countable. What we're going to do now is we're going to build a real number y, which by construction cannot be on the list, but is nevertheless a number between 0 and 1. And we had assumed that every number between 0 and 1 was on the list, in which case, if we exhibit a number which is between 0 and 1 and not on the list, we have a contradiction. Something is wrong with our reasoning. The only assumption that we had made has to be revisited, which in this case will mean that the interval 0, 1 is in fact uncountable. So the real number y that we define will be a number between 0 and 1. It will have a decimal representation, a decimal expansion, 0.y1, y2, y3, and so forth. And this is how we're going to choose the actual digits in the expansion. The ith digit of the expansion will either be 2 or 6, depending on the decimal expansion of all the terms in the list. So if the ith digit of the ith number in the list is greater than 5, the ith digit of my number y will be 2. And if it's the other way around, if the ith digit of the ith number in the list is smaller than 4, then my ith digit of the number y will be equal to 6. Now, by construction, the way this is done here, y is in the interval. If it's in the interval, and the interval is countable, it means that y should be somewhere on the list. Now, what we're going to show is that y cannot be any of the numbers. In particular, we know that y cannot be the number x1. How do we know this? The first digit of y in the decimal expansion, y1, is going to be 2 if x11, the first digit in the expansion of the first number x1, is greater than 5. And it's going to be 6 if the first digit, x11, A11 here, is smaller than or equal to 4. So by definition, y is not equal to x1 because it does not share the same first digit as x1. We know that y cannot be equal to x2 because, for the same reason, it cannot share the same second digit as x2. If it shared the same second digit, if A22 was equal to 7, for instance, it would mean that y2 would have to be equal to 7. But y2 cannot be equal to 7. If A22 is greater than 5, such as is the case when A22 is 7, y2 by construction has to be smaller than 5. In fact, we've set it as being equal to 2. It cannot share the second digit with the second number x2. This number y cannot share the nth digit with the nth element in the list. And so y cannot be on the list. If y was on the list, it would be one of those, perhaps this one here, and amongst other things, it would need to share the same nth digit. But by construction, that is impossible. There's only one possibility. The assumption we made that such a list existed in the first place was wrong. There is no list. Hence, I, the interval 0, 1, is actually uncountable. Well, look, this doesn't say that R is uncountable, but the interval I resides in the set of real numbers. I is uncountable, then R also has to be uncountable. And that's by the corollary to Theorem 8. Now here's a question for you. We've seen that Q is countable. We've seen that R is uncountable. R is infinitely larger than Q. Roughly speaking, this is what it says. What can you say about the irrational numbers? Are they countable or uncountable? Pause the video, think about it for a second. What are the options? It can be countable or they could be uncountable. Is one of those options impossible? Well, let's say that they were countable. Then you would have Q as being countable and R minus Q as being countable as well. And their union make up the real numbers. And that's what it means to say R minus Q. So we would have R as being the union of two countable sets. But then it would be easy to make a list of the real numbers. I would just start by picking the first element in the list of rationals, the first element in the list of irrational. And it would go down and alternate, and there would be my list. R would be the union of two countable sets. Here's my list for the rationals, R1, R2, R3, R4. Here's my list for the irrationals, I1, I2, I3, I4, and so forth. Then I would be able to write R basically as R1, I1, R2, I2, R3, I3, and so forth. Would have a list for the real numbers. And we know that's impossible because R is uncountable. So it's impossible for the irrationals to be countable if the rationals are countable, because the real numbers are themselves countable. And this proves that the irrational numbers are actually uncountable.